Got it? Thanks. I'll begin with a word of prayer. So, Heavenly Father, we thank you for this morning. I thank you for these students, Lord. I just pray that you be with us today. Help us to glorify you, what we do. Again, Lord, I thank you that our salvation is by your work, not by our own, Lord. If we just accept you and ask you into our heart, you give us forgiveness of our sins so freely, Lord. We thank you for that, for being a good God that you are. Let's pray, be with us today. Help us to understand a little bit more about the partial fractions technique, Lord, and also the homework on trig substitution. In my prayer, Lord Jesus. Amen. So I'm going to devote the first maybe 10 minutes of class or so to your homework questions. I wouldn't assume this will happen in future weeks. It may be the next time that you're not done with your homework, I'll just collect it, you know? So, some of you got lucky today. Let me just say that. You know who you are. So, questions? Yes, sir. Yeah? What is the what's the integral again? X squared over x squared plus what?
1 plus x squared is x squared root.
All right. And you're asked to solve via hyperbolic substitution, right?
Yes, sir.
Now, I hope you've looked at my chapter 9, because I have like 3 or 4 examples in there beyond what I showed you guys in class. And part of the reason I used the projector to show you guys that was to alert you to the fact that there are examples in my notes that you can look at, especially on this topic. But basically here, I think about, okay, so I know that cosh squared phi minus sinh squared phi is 1, right? So if you look at this tells us that cosh squared phi is equal to 1 plus sinh squared phi. Aha! So if you look at this pattern and that pattern, it makes you think, well, if I set x equals to sinh phi, I may be in business, see? Because if I set x equals to sinh phi, then what's 1 plus x squared going to be? Right, cosh squared. So that would be the substitution I make, and go from there. Just eyeballing it, I think you'd have, and I'm not going to do the, I won't work out, I mean, just let me look at it for a second here. I guess you get sinh squared phi, you get cosh phi d phi, and you divide by cosh phi. So I guess you end up with, once you make the simplification, I think you've got an integral of sinh squared to deal with. How do you integrate sinh squared phi? You say it's integral of 1/2 of, what did you say? 1 plus cosh 2 phi? Cosh squared minus 1? Oh, okay. Excuse me. And then you're like, okay, so that's, excuse me, 1/2 1 plus the hyperbolic cosine of 2 phi minus 1, excuse me, d phi, and then you can integrate that. Yeah, that's one way you could do it. Another way you could do it would just be this. This is 1/2 e to the phi minus e to the minus phi, right? So if you square this thing, you get 1/4 e to the 2 phi minus 2 plus e to the minus 2 phi. In other words, the sinh squared of phi is exactly 1/2 of cosh of 2 phi minus 1. Of course, that's exactly what you came to with your trick, which is fine. was pointing out there are different ways to come to this identity. You could even integrate the exponential function. There's tons of different ways to integrate this sinh squared function. But that's the start of it anyway. Yes, sir? 8.3.22. Integral. Interesting. Cosine to the fifth x, sine to the fifth x, dx. So what I do, this is nothing more than the integral of sine x cosine x to the fifth power dx, which is the integral of, let's see, your sine x cosine x is what? It's 1/2. So that's 1/32 sine to the fifth of 2x dx. Then I've got integral of sine to the fifth, which I can do. Es no bueno. Trigonometry. I don't know. Sine x cosine x is sine 2x over 2, right? 2 to the fifth, 32. That's one way. Another probably equally easy way would be just to go, okay, so that's the integral of cosine to the fourth x, sine to the, I'll tell you what, I'll pick on the sine. Cosine to the fifth x, sine to the fourth x, sine x dx, right, like this. And, okay, so that's the integral of 1 minus sine squared x, quantity squared, sine to the fourth x, the derivative, oh, I'm sorry, gee George, let's try that again. So that's the integral of cosine to the fifth x times 1 minus cosine squared x squared, and then, sine x dx. So I can make this minus du for u equals cosine substitution. You could do u equals sine the other way. It's kind of symmetric. That's another way you could do it. It'll give you a rather different looking answer. They're the same. Whatever floats your boat. I'm sure some of you could find a more complicated way to do this, right? Yes, sir.
I have a question about 8.3, number 8.
8.3, number 8. Sine squared cosine to the fourth. So what was your question?
I'm not sure how you get when the even numbers. I didn't really understand how you could get out of it because of the
Well, the different approaches here. I may be able to use the sine 2x trick again. That's probably the easiest way to do this one, is to go, okay, well, this is really the integral of sine x cosine x squared times cosine squared x dx, right? At which point I can go, aha, well, that's really just the integral of sine, what? Sine of 2x over 2 quantity squared, right? And what's an identity for cosine squared in terms of cosine? Well, that's times 1/2, 1 plus cosine of 2x dx, right? So if you distribute that out, you've got an integral of sine squared, which you can do, and you've got an integral of sine squared times cosine, which you can do. The less insightful way of doing this, which is the way I will do it if I'm tired and not thinking, or just really want to write a lot, is that you could look at this as 1 minus cosine of 2x divided by 2 times 1 plus cosine of 2x over 2 squared dx. And then you could FOIL that thing out, and you'd get cosine squareds and such, and then you can break those down to cosines of 4x, and eventually you'd work your way down to like cosines of 6x and stuff. You could also do it by repeated application of double angle formulas like that in the red. I don't recommend it. It's not impossible. I mean, you could do it basically in the same spirit we did the cosine to the fourth integral. Or sine to the fourth. I forget which one I did in here. So not knowing trigonometry can hurt you in this homework, right? It makes work for you. The more you know, the less work you have to do in terms of these things, right? I guess you do have to have the insight of where you're going and what you know how to do, and that only really comes with working more problems, unfortunately. At the moment, I have no ethical solution. I mean, like, even an unethical solution. Maybe in the future there'll be a chip. I can just stick it in your head, and like, you don't have to learn it. We just like plug it in there and you'll be good to go. Along with the obligatory martial arts skills and such, but yes. It's too early? Okay, fine. There must be other questions. Yes, sir.
Number 48 from
Ah, yes. A tasty problem. So here you're asked to calculate the volume of a donut. The donut has big radius B, and it has little radius A. So like, for example, this is x minus b squared plus y squared equals to a squared. That's the equation of that. You rotate that thing around the y-axis, right? And you get a torus, right? And it says to calculate the volume by the method of shells. So what you want to do is chop that thing up into cylindrical shells. So here's a typical one. The thickness of this, of course, will be dx. The radius will be x. So if I draw the cylindrical shell down here, like so, I've got radius x. I've got height h. Now h is equal to 2 times the square root of a squared minus x minus b squared. You see why that is? It's because the top of that circle, right, the semicircle, the northern semicircle, if you like, I'm about to make it purple. This guy right here, is exactly y equals the square root of a squared minus x minus b quantity squared. Right? So then by symmetry, the height h, which is here, right, is twice that. What's the volume of this shell? dv? 2 pi x times h dx, which of course is 4 pi x square root of a squared minus x minus b quantity squared dx. For which x? This is for b minus a less than or equal to x less than or equal to b plus a. Because the circle there, the furthest it goes to the left or to the right, respectively, is b plus a and b minus a. So then what? Well, that's the volume of a typical infinitesimal shell. If you look at it, so you just add up the volumes of all these shells, and that gives you the total volume. You gotta integrate that thing from b minus a to b plus a. If you think about that, that makes good sense. If you plug in x equals b plus or minus a, you get a squared minus a squared for h. So the h drops to 0 at the endpoints, which is good. That means our setup is at least on point. And of course, what kind of substitution would you make? It's like a number squared minus a variable squared. That goes back to the first kind of trig substitution we did. I think if you make a x minus b equals a sine theta substitution, it'll serve you well. So I think x minus b equals to a sine theta. Helpful. Yes, sir. Sorry. Excuse me. 8.273. Which part? Part A or part B? Okay. So this is a rather crafty idea. Basically, the idea of this problem is that if you're integrating something, right, and you kind of know where you're going, then you can make an educated guess and just do algebra. This is a common technique in differential equations. So I'm not going to work exactly the problem. I'm going to work something very similar to it, like this. So if I have x squared e to the x dx, you integrate by parts, what's going to happen? The first integration by parts will pop out like an x squared e to the x. The second integration by parts is going to reduce the order one more. You'll have like an x e to the x term. And then the second integration by parts will get rid of it, and you'll be down to integral of e to the x. What you're going to end up with is just some kind of linear combination of e to the x e to the x, and x squared e to the x. So if you're not interested in the integration by parts procedure, you can just kind of go, oh, okay, well, this is going to have to be something like a e to the x plus bx e to the x plus c x squared e to the x. That's going to be what's going to pop out. And then, plus a constant, which we don't care about that much for this. So what I do is if I want that to be true, that means the derivative with respect to x of a e to the x plus b x e to the x plus c x squared e to the x, that must be equal to x squared e to the x. That's what we want. That's what it means for it to be an antiderivative of x squared e to the x. Now, if you're not getting this problem, odds are that you're not doing the product rule over here. Maybe, at least I've talked to one other person today who reason they weren't getting this problem was because they weren't doing the product rule here. So a to the x is the derivative of that, right? But then I get b times what? Times e to the x plus x e to the x by the product rule, plus c times, 2x e to the x plus x squared e to the x by the product rule. That's all equal to x squared e to the x. If I divide this by e to the x, what do I get? I get a plus b plus x times b plus 2c plus x squared times c, or cx squared, I don't know, equals x squared. And then I've got this quadratic is equal to that quadratic. I can equate coefficients, right? Like, you can see from this immediately c equals to 1, and a plus b equals to 0, b plus 2c is equal to 0. So if c is equal to 1, this tells me b is equal to minus 2, and then that tells me that a is equal to 2. And so I learned that the integral of x squared e to the x dx is in fact x squared e to the x minus 2x e to the x plus 2 e to the x plus a constant. All without integrating by parts. So the point is to take them on face value that that's an educated guess for the integral. You differentiate it, set it equal to the integrand, and then just equate coefficients. It'll tell you what the a, b, c, and d there is. Does that make sense? It's kind of a sneaky trick. That's actually, I think, faster than integration by parts for this particular problem. It won't be faster until you understand what you're doing, but once you understand what you're doing, you should understand that this technique for this particular kind of integral is actually very useful. Yep.
Back to that problem, how do you not make this b equals 0?
I've got two polynomials, right? I've got a quadratic I've got a quadratic polynomial on this side, I've got a quadratic polynomial on that side. The only way two quadratic polynomials can be equal is if their coefficients match. If you want me to prove that, we could put x equal to 0, we get the constants match. Differentiate once, set x equal to 0, that proves the linear terms match. Differentiate twice, put x equal to 0, you get that the coefficients of x squared match. So, I mean, to prove that polynomials, you can equate coefficients, you can prove by calculus, successive evaluation, and differentiation at 0. Other questions? Yes, sir.
Did you already go over constant D8 and C?
Yeah, I think we already did that one another day. Yep. Other questions? I mean, in short, you should start with the integral of f prime prime times x minus b and go from there. Let your dv be f prime prime of x dx. Yes, sir. 8.4, number 44. Well, you guys are just this one, yes. So here you're asked to calculate the area of this guy. This height being h, this circle being x squared plus y squared equals to r squared for r, little r being some positive constant. So find the area of the shaded region. Number 44 in section 8.4. Who put that there? Curious. All right, so basically, I just need to figure out what's this and what's that. I'll let you figure that out. What are those points of intersection? And then I just got to integrate the square root of r squared minus x squared minus h dx from a to b, and that's it. See, because the typical area, little dA there, you're adding them up, summing them up to calculate the area. So a typical area is like this. dA is, y minus h dx, where y is the positive solution to the circle. And of course, then you can see why this is in the integration by trig substitution section, because that integral is done with a trig substitution. But you want to leave your answer in terms of h and little r, right? You want to simplify it as much as you can. Other questions? Okay, I'm going to move on then. Well, that 10 minutes turned into 25 minutes. But I hope it was productive for you guys. Okay, so continuing on with the topic of partial fractions, I'm going to do a couple more examples for you today. I think we'll be still doing partial fractions tomorrow. We'll see. Past partial fractions, we kind of have hybrid problems, which are some sort of mixture of the technique of partial fractions and our other techniques. So it's even more fun when we can combine these techniques and do problems which are based on combinations of these techniques. Let me start by just talking about this example over here. So, all right, so the question is, what's the integral of dx over x squared plus 5x plus 6? What is that? That's the question. So this is a pretty standard partial fractions technique problem. I factor to the denominator as x plus 3 times x plus 2. All right. And once I do that, the partial fractions decomposition then, part of that big theorem I tried to write out for you last class, all those different cases, is that I write a over x plus 3 plus b over x plus 2. These a and b's are undetermined coefficients. I need to figure out what those are to like basically undo the common denominatoring of x1 over x plus 2 and something over x plus 3. All right. So what I do is I multiply this equation in purple by the denominator, x plus 3 over x plus 2. When I do that, the x plus 3 term cancels and leaves me just x plus 2 with the a. Conversely, on the b, the x plus 2's cancel and leave me x plus 3. Then what's my next move? Yeah, plug in the zeros. So x equals minus 2 and x equals minus 3. It is somewhat disconcerting. I'm plugging in the values for which the original equation didn't make sense. And yet it works. There's a homework problem for you. I don't think I assigned it, but you know, there's something somewhat malevolent here. The fact that we're plugging in the points where, I mean, you've been graded over the coals. Don't plug in the value it's not defined for it. If you divide by something that's 0, then you lose information. So then we get to calculus 2, and then we're multiplying by denominator, and then we're sticking in the values where we just told you it doesn't make sense up here. It works though. So x equals minus 2 gives me 0 and b, and x equals minus 3 gives us that. And so we find a is equal to minus 1, b is equal to 1. You plug them back in, and you get that the integral is actually the integral of minus 1 over x plus 3 plus 1 over x plus 2. And then u substitution does the finishing blow by u substitutions. U equals x plus 3, u equals x plus 2. And there you have it. This is a pretty standard partial fractions problem. Maybe the interesting non-trivial variety. Now, if you think back to chapter 7, we already had a way to do these kinds of integrals, right? Because if I have this, I can complete the square. And if I can complete the square, I can go, wait a second, that's a hyperbolic cough substitution. Or you could make a hyperbolic tangent substitution just the same, I believe. I do it at the end. So you could make a hyperbolic substitution, do these steps, and you'd be left with something like inverse hyperbolic cotangent of 2x plus 5 plus a constant. So if we can just do this, why do we need this? Right? So I was thinking about this a little bit this morning, and I think the answer is basically the following. I mean, both of these answers have their place, and sometimes they agree, but not always. So what's this function look like? You got x equals minus 3. You got x equals minus 2, right? If I look at y equals 1 over x squared plus 5x plus 6, where are the zeros of this? Where is this function 0? Saying f of x, of course, is 1 over x squared plus 5x plus 6 is the function I'm talking about, but it's never 0, right, never 0. This is never 0. You can't, the only way you can get a fraction to be 0 is if the numerator is 0. The numerator is 1. Game over. There's no zeros. It has vertical asymptotes at plus or minus 3. I mean, minus 2 and plus minus 3, right? What does the graph look like? Asymptotically, it goes to 0, right? This is a quadratic. Eventually, that's positive. So it must look like this for the long-term behavior. And also, these are like linear terms, which means the signs flip. This totally dominates near minus 3. This totally dominates near minus 2. So it's got to look something like this. That's the graph. what's in black here is the antiderivative of this function everywhere that it's defined. All right? Don't try to apply the fundamental theorem of calculus across an asymptote. That won't go well for you. But if you focus your attention to any of the connected intervals which define the domain of the function, you're good to go. And this, on the other hand, remember, minus 1 less than 2x plus 5 less than 1 is its domain of applicability. That's where the inverse hyperbolic tangent or inverse hyperbolic cotangent live. What is this? Aha! This answer only makes sense where? In between the asymptotes. So you see, Chapter 7 gave us an answer. And it was a good answer, because it didn't require us to learn the technique of partial fractions. But at the same time, it was a limited answer, because it only works up in here. Whereas this is general. So it's a nicer answer. Anyway, there you go. So there's one example. Let's do another. Any questions before I move on to our next example, which will be slightly more insidious? Actually, a lot more. Yes? Did I plug in for dx? By the way, is the green on the mic on top, on light, is it still green up? Okay, good. Oh, the derivative of coth is minus hyperbolic it's minus hyperbolic cosecant squared d phi, and then the there's a half that was riding along, so I just basically differentiate that to get what's this right here is dx. What's in the numerator is exactly dx written in terms of the new variable. Again, when the hyperbolic or the trigonometric substitution works out like this, it kind of is like that's, by the way, kind of a signal. Oh, wait a minute. We could have seen this in a previous chapter, just as a basic elementary integral when we were studying inverse trigonometric functions or inverse hyperbolic functions. You know, it's basically like a u substitution over one of our elementary inverse hyperbolic. But anyway, I don't feel too bad about not spending more time on that because it's somewhat limited in its application, like I'm showing you here. All right. Let's see here. So, here's a problem. We'd like to find the partial fractions decomposition for this. First of all, I don't need to do long division because we've got a quartic over a cubic. It's a proper rational function. Maybe tomorrow I'll finally do some long division. I don't think it's happening today. Sorry about that. So we would look something like a plus b times x minus 1 divided by x squared. Well, you know, x minus 1 quantity squared. So I completed the square on that quadratic to show you that it's irreducible. It's prime. It can't be factored over the reals. And then plus c over x minus 3 plus d over x minus 4. All right. The reason I've written it in this way, rather than say the other terms first, it will become clear after the next example. It's a joke. Anyway, so there's the setup. I mean, that's not a joke. Any questions about this? So this is partial fractions decomposition. Now what do? I multiply the denominator through here and see what it gives me. So that's going to give me 8x cubed minus 57x squared plus 94x. I'm just copying the numerator down again. Minus 41 is equal to a plus b times x minus 1, brackets, times x minus 3 times x minus 4 plus c times x minus 4 times the quadratic plus d times x minus 3 times the quadratic. And I'm going to call this whole thing star. This problem is an argument for calculating in landscape. You know what I mean? Like sideways. Okay, so. Now, the start of my solution is going to be rather unsurprising. So what I'm going to do is I'm going to take star, and I'm going to do what? I'm going to set x equals to 3. What's that going to tell me? 8 times 27 minus 57 times 9 plus 94 times 3 minus 41 is equal to, well, that's 0. That's 0. Only c is left. C times 3 minus 4 times 9 minus 6 plus 5. You put in the numbers, you work it out, you get c is equal to 7. You see that? I mean, you punch it in the calculator, you work it out, you'll get 7. There's nothing mysterious here, right? I've got number equals c times another number. I can solve for dividing by coefficient of c, right? If it makes you feel better, you can get your calculator out and plug in the numbers and see I'm not lying to you. What happens when I plug in x equal to 4? 8 times 64 minus 57 times 16 plus 94 times 4 minus 41. And now, when I plug in 4, that term is 0. That term is 0. Only the d term survives. d times 4 minus 3 times 16 minus 8 plus 5. And if you plug in the numbers, what you'll get is d is equal to minus 5. And at this point, we're out of roots, right? I mean, unless you want to plug in complex numbers. But my experience is that doesn't go well in here. Let me not do that. So how can you get more equations to figure out what the other two constants are? How do you figure out what a and b are? This equation, star has to be true for all x, as it happens. You're like, even the ones where it's not defined, like 3 and 4, yeah, you can prove that. I won't, but it is in fact true. Well, various things exist. I mean, so here's one way you can do it, is you can just pick on a particular coefficient. Like look at x cubed. What are the x cubed terms on both sides? They have to match. Just like the homework problem we were talking about, number, what was it, 71 or 72? You asked me, what was it, number 72? That one we were equating coefficients. The same idea here, right? Except there's no exponentials to divide by. We're already starting with a cubic equation equals another cubic equation. In order for those to be equal, they have to have matching coefficients. Now, you could actually multiply this all out, but why do that? What do you get from that? A lot of writing, right? What else do you get from it? I guess you get an easier next step, but there's a lot of writing and a lot of opportunities for making mistakes. There's also opportunities for making mistakes in what I'm about to do, but less writing at least. So 8 is the coefficient of x cubed. What are the x cubed terms over here? Oh, x, b. Anything else? X times x squared plus c. Anything else? Just this one, plus d. Hey, wait a minute. I already know c and d. What's that mean? B is equal to 8 minus c minus d, right? Which is what? 8 plus 5 minus 7. Other way around, sorry. Minus 7 plus 5, which is what? 6. B is equal to 6. Now, in the earlier section, when I tried this problem out, I tried to equate coefficients of x squared. I found out that that's kind of a pain. So let me adopt yet a different approach here. What we're looking for now is just another equation which is independent from the three we already have. Our goal is to determine what in the world the value of a is, right? So what's something easy you could do to this problem that we haven't done yet? I'll tell you what's easy. Plug in x equal to 0. X equal to 0 is easy to think about. So let's just do that. X equals to 0. You say, but that's not in the problem. There's no x equal to 0 term here, right? Why am I doing that? Like I said, x equal to 0 is easy arithmetic, right? How about this side? What's x equal to 0? What's this? Minus 41. All right. X equal to 0 over here. What do you get? A minus b times what? Times 12, right? And then here we get minus 4c times what? 5. And then minus 3d times 5. And then solve for a. So a is equal to minus 41. I guess I should put in the numbers here before I do that. What is this? So minus 41 is equal to 12a minus 12b minus 20c minus 15d, which is what? Minus 41 is equal to 12a. What was b? 6. 6 times 12 minus 72. C was what? 7 minus 140. D was what? 5 plus 75. So what's A equal to? Minus 41 plus 72 plus 140 minus 75, all divided by 12. What are we doing? What is this? What is it? 8. Yes. Aha. So apparently this is 8 plus 6 times x minus 1 over x minus 1 quantity squared plus 4 plus 7 over x minus 3 minus 5 over x minus 4. There you have it. You're like, I thought this was calculus too. Seems like all we're doing in here is algebra. I know, right? That is true. Most of calculus 2, the interesting part of calculus 2 is in fact algebra. Of course, now we can integrate, right, if we wanted to. Yes, sir?
Just to rehash, the x cubed, you use that because it's the highest power.
Right. Yeah, it's an easy thing to pick off. Other things you have to think harder about, like the square or the x term, there's multiple ways of getting those from each of these products. Whereas each one of these summands, there's only one way to get the cube. The highest power is usually easier to see. Sometimes the lowest power also. It's also easy to see constant terms, right? Like the only way to get a constant here is from the minus 1, the minus 3, the minus 4, and the a. Of course, this is really picking off the constant term anyway.
Yeah.
Yeah. My next example, which is important for me to get to today, believe it or not. Oh, where did I put it? Oh, over here. Duh. Is a rather different animal altogether. Here it is. 3x squared minus 12x plus 21 divided by x minus 2 quantity cubed. Fortunately, again, a proper rational function. So there's hope for us. Now, so what's the partial fractions decomposition here? We try out a over x minus 2 plus b over x minus 2 quantity squared plus c over x minus 2 quantity cubed. Our goal, your mission if you choose to accept it, is to find a, b, and c. First move. I know it's very boring. It's always the same first move. Let's see here. 3x squared minus 12x plus 21 equals to what? A times x minus 2 squared plus b times x minus 2 plus c. So I multiplied both sides by x minus 2 cubed. Let us call this equation star. No, I tell you, I'm tired of star. Pac-Man. There we go. Brought him back. What happens if you take Pac-Man and you put in 2? I'm ashamed. This is the first time I've ever done that. I've taught calculus for years and years and years. Why didn't I ever think of this before? This is so obvious. Everything I was doing before this lecture, before this moment, was wrong. This is right. Okay, so that's 3 times 4 minus 12 times 2 plus 21 equals to c. Oh, man, that's awesome. Okay, so c is equal to what? What'd you get? 9? Yeah. Now here's a really neat trick that works. If we take the derivative of Pac-Man with respect to x, we get what?
Can you explain how you got 9 from adding that? Should it be 12 minus 24 plus 21?
33 minus 24 is 9. Es bueno.
So that's 3 times 4.
Yeah. Because 2 squared is 4. Let me keep going. I'm going to run out of time otherwise. So then what? What's this? I can do what? So Pac-Man prime eating a 2 gives me what? 12 minus 12, right? Equals to what? B. B is equal to 0. And what's Pac-Man prime prime? We get what? 6 is equal to 2a. So I don't even need to plug in something. I can already tell you a is equal to 3. And there you have it. So we've got 3 over x minus 2. There's no, plus 0 over x minus 2. I wouldn't usually write this. And then plus 9 over x minus 2 quantity cubed. There you go. So my question to you is, who can I talk to? I said, who can I talk to? Jenny, obviously. No, I guess I need to outline. Not obvious enough yet. There you go. Oh, happy convocation to you all. Yes. No convo? We can just do calculus 2 for another hour.